All right, so let's review some stationary distribution and asymptotics. As you know, you can write the stationary distribution as Pi, Pij. And a very good example could be defined like this. You say that the P tilde of J is the expected time, that assume that you start from I0, of number of times, number of visits to J before some time. For example, time t plus I0. Such that J is not I. And P tilde of I0 is 1. We can easily check that Pi is a stationary distribution. So if you define it by Pi tilde of I over summation over all Pj, so this is a very good example of a stationary distribution. You can check that this is a stationary distribution. And it is intuitively, it is very, you can see it that it's very intuitive, and for example, J, the vertex J is here, and you start from some vertex I0, and it goes several directions, and after that it hits J. So number of visits that it hits J, for example, it could go there, and after several time it hits J again. So the expected number of such visits, expected number of visits to J before some time, some stopping time, that stopping time could be anything. It could be the minimum time that it hits I0. It returns to I0. And so this expectation is could be defined as a stationary distribution. And we will see it in several cases. And the Ergodic Theorem, that is very important in statistical mechanics and in mathematics of Markov chains, also mathematics of chaos in dynamical systems. So this theorem is very important. It says that let Ni of t be number of visits to state I during time 0, 1, and t minus 1. Then for any initial distribution that you say Ni of t over t, so Ni is just the number of visits to state I. So this converges to Pi almost surely as t goes to infinity. So you have a sense of gut feeling that Pi is some kind of space average, and the number of visits to I divided by t is gives you a sense of time average. So they converge to each other. Now I give you one proposition, and after that I give you another proposition that generalizes that, and you will see that several lemmas are just application of this important proposition. So the simple interpretation of the proposition that I want to say is this proposition. So first I start by a simple proposition. It says that the expectation of first, if you start from vertex I, the expectation of the number of visits to j before some stopping time s is equal to pi j, expectation of that stopping time. So s is just the stopping time, and we just know that expectation of that is not infinity, is finite. And you start with I, vertex I, and so from vertex I to vertex j, the number of visits to j before some time s. S could be anything. Sometimes it's a heating time, sometimes it's a return time, but it is but always you should assume that it's a stopping time. Otherwise, your mathematics and probability does not work. So the number of visits to j before time I, so as you see, there are many paths. It could go there, it could go. So there are many paths from I to j, but the number of visits, expectation of number of visits to j before time s is pi j, and it is very intuitive because when j has a lot of, when the degree of j is too much, so you expect that the number of visits to j is very much, because there are many ways that you can go to j. There are many paths to go to j. So your gut feeling says that, okay, I understand that it should be proportional to pi j. And then you can also say that your gut feeling says that it should be proportional to expectation of that stopping time, because it depends how close your I is to j. And because for example, s could be hitting some set A. So the expectation of s could be proportional to number of visits to j. If you start from I and then you go to j. So your gut feeling says that it should be proportional to both of them. And this is the proposition. And so in general, we want to generalize the theorem. So the theorem that I said, that expectation of number of visits to j before some stopping time s equal to pi j ei s. So in the new proposition that I want to say, I just change this. I want to generalize this. ei to e theta, because theta is a probability distribution. So instead of starting from some vertex, some fixed vertex, you are starting from a initial distribution. It's like starting from a uniform distribution. So starting from a distribution rather than just starting from a fixed vertex. So it is not biased. It's trying to say that distribution, no matter what vertex you start off, you get the same thing. And here, the I again is replaced by theta. So the new proposition that I want to prove is that the expectation of the number of visits to j before time s is equal to pi j e theta s. So the same proposition as I said. So how can we prove this? So I said that your gut feeling says that it should be proportional to j, because the degree of j shows that how easy it is to reach j, and also it should be proportional to this one. So in order to prove that, first we should say that let's imagine rho j. Let's define rho j by expectation if we start from theta distribution of number of visits to J before time S. So rho K is the same thing because you just replace J with anything such as K. So rho K is the same thing, number of visits to K before time S. So if we just prove that rho J P J K is equal to rho K, then by uniqueness of this stationary distribution, saying that because a stationary distribution is like this, okay, so it should be proportional to your stationary distribution because it is unique. Stationary distribution is unique. So there should be some constant C such that, for example, rho is something here, and so it's 1 by number of vertices of your graph, and pi is another distribution, but it is a stationary distribution. It's something else, and it is 1 times number of vertices. So pi, so at any index, then there should be proportional to each other, C times each other. And after that, it's very easy because, so as I said, rho J P J K is equal to rho K. So this is just C pi K, and as I said, it's proportional, so it's just pi J, and you can also say that pi J rho J K as usual equal to pi K. So in this way, you say that they should be proportional to it. So C times number of the stationary distribution. So rho should be proportional to stationary distribution. So as I said, we just need to prove this. Proving this, and the goal is just to find a positive number C. Let's say we choose it as rho K. C is well defined just because if you sum rho K, you get expectation of S, because expectation of S is 1 times probability of your stopping time. So you are convinced that it is enough to show that it is enough to prove that rho J P J K is equal to rho K, summation over J. So the proof is very simple because we just use some algebra. So from t equal to 0 to infinity. So instead of rho K, I can say that it is the probability that if you start from theta, your xt could be k and your stopping time is greater than t. So you go from I to j, sometimes like this, sometimes through this pass, sometimes through this pass, which is much longer. It takes time to reach j. And so this probability, you can write it as, since p theta of xs equal to k is pi. If you start from theta, then no matter if you start from x0 is k is equal to xs is equal to k. So the probability, because theta is a distribution, and x0, so you may get to k from different times, and so this is equal to p theta. Now xt plus 1. So if you start from t plus 1, it is the same things. Because you can start from t plus 1. You can start from t plus 2. And still your stopping time is greater than t. It means that you have not reached your stopping time. Still, you have not reached your stopping time. And then you can just rewrite it by saying that summation over j p theta xt is equal to j, and still you are less than your stopping time. You can continue, but xt plus 1 is k. So as I said, xt plus 1 is k, but your previous state, you could sum over that, because your previous state could be anything. So we sum over that. And Markov property appears like this, because this is just equal to t equal to 0 and summation over j of p theta xt equal to j, and still you have time, still you have less than your stopping time, and pjk, and I can say that this is just rho j. So from here to here, I just use Markov property. And from here to here, I just say that this is rho j. So the final sum is simplified to rho j p j k. And the proof is complete. So I can say that you go from I to k, but first you go to j, and then from j you go to k. So it's a time. So there are many paths from I to j. We respect that at time t, for example, we are at state j, and at time, for example, t plus 1, we are at start k. And there are many paths from j to k as well. So s is a stopping time, and your s is greater than t. So it could be any stopping time. For example, first return time, ti plus. This is a stopping time. So this could be a stopping time. And I will show you that using different stopping times, if you apply different stopping times to this proposition, you can get several lemmas. You can even invent your own lemma by just using a different stopping time. So this proposition is interesting because it says that for any stopping time, this proposition holds. I review that the expectation of number of visits to j before that stopping time s is equal to pi j e. If you start from theta distribution, the expectation of your stopping time. So no matter what your s is, you get this proposition. So if you just replace this stopping time by anything that you like, for example, hitting a set, hitting a vertex, exiting from a set, anything that you like as a stopping time, everything that you need in your problem as a stopping time, you get a new lemma, a new result. And I will prove these results one after the other, because I'm just replacing s with some stopping time. I get different lemmas. For example, a lemma could be saying that expectation, if I start from I, so the expectation of return to I, this expectation is the inverse to the